Hi everyone. How are we doing? Well, first of all, I'd like to give it up for H2HC. Like, this conference is just gorgeous. Just nice. So today, I'm going to talk about this thing, SWAPwn. SWAPwn. I don't even know how you pronounce that. But yeah, it's a faster way for detecting double fetch vulnerabilities. And it's by me, sure. So this is a disclaimer that was put by Intel Legal. And I do not really speak lawyer language, but it kind of means that it has nothing to do with Intel. I was doing it in my spare time. They have no responsibility for it. Yeah, but for proper explanation, I suggest you to visit Marion's talk, which is going to be the next talk after lunch, I believe. Yeah, and she has more knowledge about this one. But still, yeah, it has nothing to do with Intel. And who am I? Yes, I'm a security researcher at Intel Corporation. That's why I had to put this disclaimer first. And I like Windows kernel. It's like not that much to talk about me. Yeah. So the double fetch vulnerabilities, what that is. Yeah, I'm going to come up with a different sample. For example, imagine the situation. Two guys going to the store. They want to buy something really expensive. Let's say it be a new video card that makes your images all bright and shiny. Yeah, so the point is, they go to the store, they walk around, they're choosing all the options. And then, yeah, okay, you came up with a video card module you want to have, and then you buy it, you go to the register, and you count the money, your cash, you give it to the sales assistant, and then you're like, wait, it's too expensive. I know it's cool, but it's too expensive. No, I cannot do it. And you're like, no, you know, I'm not gonna do it. Here's your video card back, give me my cash back. It's just, I cannot. But at the very same moment, a friend of this guy is like, no, you should buy it because you wanted to have it. Like, you will whine all the time. It's like, and you're like, I mean, not you, the guy is like, okay, he gives the cash back to the sales assistant, gets the video card, and the guys walk away. But the thing is, the second time he gave a cash, he actually gave not a cash, but for example, this one with Rodrigo's smiley face. Yeah, so that was my example of double fetch vulnerabilities, because the first time the sales assistant fetched the money, it was actual real money. And the second time, since, yeah, he had already checked that the money was real, so he just accepted the fake ones. So the same happens here, as in this example. We got some structure, which is dereferenced in the kernel mode driver. And for example, yeah, the closest example to a real world is checking the size. So you check the size, and then a different tree concurrently tries to modify this field. And this is where the vulnerability kicks in, because we think that we already checked the size, but for example, when we try to use it sometime later, it is already different. So it leads to buffer overflows, right? And that's the way you actually exploit this thing. So in here, we got two sequential references to the same address. So the proper way would be to get the size, to cache it, not the size, but the whole structure. To cache it locally, and then do the checks. Because in this case, we would be sure that no one would modify the structure in this small window. It's small, but it's still a window, and you can win this race. So how do we track this situation? So I'm not the first one who actually does that. The most famous work, I believe, is done by Mateusz Jurujczyk and Ginwile Colwyn from Google Project Zero. And they presented this talk like a couple of years ago already, and the work in progress still, I believe. So what they did, the project was called SWAPwn. I'm not sure about the pronunciation, sorry about that in advance, but still. Box is a full system emulator. I don't know if you've ever tried that, but it emulates the whole system. So they took this thing and they instrumented it because, yeah, it's all in software. And they do the instrumentation in the way they actually record all the references from the kernel mode to user mode. And they also track the timestamps. And for example, if we have two sequential accesses from a kernel mode to user mode, we just can check the timestamps. And if it's small, relatively, this is like to be determined for each and every system. And if it's small, that means that possibly in this point of code, there was a double dereference that might lead to a double fetch vulnerability. But the drawback of this method is, since it's a whole system instrumentation and everything is done in software, it is really, really slow. Like from their presentation, the Windows 7 boot up process would take like several hours. So it's a little bit slow. For my situation, I didn't have a need to instrument the whole system since I was checking some like very particular drivers. I know what I was looking for. So I was just checking some exact drivers. So I needed a faster way because, you know, instrument the whole system to check just one driver is a little overhead. So yeah, I think like what are the different ways to track the kernel mode accesses to the user mode memory? And then I remembered this useful feature of Intel processors. It is called SMAP, which is Supervisor Mode Access Prevention. So what it does, the way Windows distinguishes the kernel memory and the user memory is based on the hardware feature, actually. Because in the page table entry, there is a bit which shows us whether it's a user page or a supervisor page. And we can interpret this one like user mode is a user mode page and supervisor is a kernel mode page. And what it does is when a code runs in ring 0, that means it's a kernel mode code. When this code tries to access a user mode page, which means that it has user mode bit set in page table entry, a page fault is raised. As simple as that. So this feature is configured by the control register number 4, bit 21, I guess, yeah. And it's called basically SMAP. This technology is coupled with these two instructions. It's stack clock, yeah. What these instructions do is they actually set AC flag in the E flag register or clear this flag. So the way it works, if you set this flag, it is called access check, I guess. But we'll talk about this later. The way it works is when you set this flag, the SMAP temporarily doesn't work. So even if you're running in kernel and you reference the user mode memory and this bit is set, nothing's going to happen. No page fault is raised. And when you clear, it is enabled again, and it works as it's supposed to work. And since Windows does not utilize this feature yet, I'm saying yet because in the latest Windows Insider builds, it is already used, but like in a limited way. So I was like, the Windows doesn't use this, so yeah, we should try that, because that's exactly the thing I want to track. And yeah, so the idea is, as I said before, to track kernel reference to the user mode memory. And tracking this one, we gather the necessary information, like the code address that caused an exception, of course, because we need to know where is the point of code which actually does the double fetch or double reference to the user mode memory. Of course, we log what address was being accessed, yeah, and a timestamp, of course, because it happens really quick. And we need to track the timestamps to find out whether it was a consecutive reference of the user mode memory, or just it was like different references in different points of code and in different time. And we gather this information and we actually apply a filtering, because when we enable SMAP feature, we're actually tracking all kernel mode accesses, which means all the drivers, the kernel itself, right? But we don't need all of that. We need a specific driver to track. So that's why we can apply filtering in real time. That means when the page fault is raised, you check the faulting instruction pointer against the range of addresses. So, for example, my driver is loaded somewhere in memory between 10,000 and 20,000. So if a page fault handler happens within this range, yes, it's our case. We track it. And it also increases performance, because if you apply filtering later, it's already a little too late, because the performance goes down as you track references, not like later, right? Which makes sense. And I was thinking about the ways to implement this feature. The first one I came up with is actually do it using the debugger script. And to be precise, using Python scripting, like PyKD plugin for WINDBG, because it offers more functionality than a standard WINDBG scripting language. So I was thinking, yeah, the algorithm would be enable SMAP for all the cores, place a breakpoint on key page fault function, which is a page fault handler on Windows, right? And then when it's triggered, we should check whether it was caused by a SMAP violation. We log everything, we disable SMAP, and we perform a single step. Like why? Because we need the system to be running, not to be stuck in the loop when it tries to access user mode memory, and we just lock an infinite loop. Now it's like the standard resumes cycle as if it was in some sort of debugger. So you temporarily disable the SMAP tracking, you do a single step, that's how you are able to track the further kernel mode references to the user mode memory. Yeah, and we just do the loop. Yeah, and this one looks fine. And the advantages are, well, it is supposed to be the fastest way to implement this, right? Because it's a plugin, you place a breakpoint, you do some coding to react to those breakpoints. Yeah, and it may be the easiest way as well, because debugger does all this stuff for you already. But it also has the drawbacks. First of all, it's a debug transport latency, because we're talking about WINDBG kernel mode debugging latency, because the way it works, it has two different machines, or a virtual machine, which is still a different machine. And those two are connected with some transport, like serial connection, USB debug cable, FireWire, network card. But even with the network card, there is a latency. When you try to transfer data from one machine to another, it accumulates, and it gives us a real delay in sending the information. Even though the transfer process is fast, there are delays, which causes the target system to slow down, because the time is wasted on sending something. And the second drawback, which actually forced me to switch my approach to something else, was it wasn't stable. I'm not sure about the real source of the problem of this one, so I'm not going to elaborate on this, because I was not really debugging why it fails. It seemed to me like it's not too thread safe, but still, yeah, it fails a lot. So, yeah, the last point is also it is not thread safe in terms of we're disabling SMAP. How we do that? We turn off the SMAP bit in CR4 register. The CR4 register is not a part of a thread context. It's just a system control register. It is set once, and it's mostly not modified during the lifetime of the operating system. So what might happen? Imagine I'm logging some thread, I disable SMAP, and then this Windows scheduler schedules another thread, and it is running with SMAP disabled. So basically we're losing some events which we are supposed to be tracking, yeah, because for every thread we assume that SMAP works, but yeah, it might happen that it might not be the case because of the scheduler. So yeah, let's come up with something else. So the different approach would be also a debugger plugin, but that would work in a little different way. Same as before, we enable SMAP, but this time we implement a custom page fault handler for the Windows operating system, a custom debug trap or fault handler. It is just called this way because if you look at Intel Software Development Manual, the interrupt vector 1 is called like debug trap or fault because it either can be a trap or a fault. So it's just a matter of name. And what we do, so we've implemented the custom exception handlers, and we patch system handlers, and then we go. And then our payload does all the job, and we have nothing to worry about. And we just receive the result into our debugger. Yeah. So the advantages: the target operating system operates way faster. Why? Because we're not catching any breakpoints. Like in previous scenario, we were setting breakpoints, and so the breakpoint was hit. Again, there's a latency in a kernel debugger transport, which accumulates, and while the debugger reacts to this breakpoint, time goes, right? So we're wasting our time on this latency. So in this case, it operates way faster because there are no breakpoints, so nothing for a debugger to react on, right? And the second point is we're patching the exception handlers, which is something you should not really do. And Windows kernel agrees on that because there is a special mechanism, which is, we all know, and it's called the patch guard, something that monitors the patches on Windows kernel, and then if it finds that something was patched, it just shows us blue screen with the appropriate code, right? But since we're in a debugging mode, when we debug operating system, patch guard does not work. Because think of it, if we need to place a breakpoint, we actually have to patch the memory, right? But if we patch the memory, whoops, we're all broken. So the patch guard is disabled, and it's pretty convenient in our case, because we're using KD, we're patching system exception handlers, and we just don't care. Patch guard will not complain about it. I think it's a good thing. So about the drawbacks. Yeah, it is still not the fastest way of execution, because the way it is supposed to work is in our custom exception handler, we're sending the information about the event to the debugger. And here we go. The kernel debugger protocol and transport latency shows up again. So simply speaking, we do the DBG print. We call the DBG print function from Windows kernel, from the target Windows kernel. And it shows some message to the debugger. And as it transfers this message to the debugger, the time goes. Yeah, because this process is not instant. And we also require a kernel debugger, which is, I'm not really sure if it's a drawback, because I don't know, I like kernel debuggers. So that leads to the last approach I was thinking of, and it's basically the autonomous kernel mode driver. So we do all the same stuff we did in the previous approach, but we don't use the kernel debugger. We do this from the kernel module, right? And the advantage is obvious. It is maximum target operating system execution speed, because we don't have to send anything to the debugger back and forth. And yeah, the logging is local. And that's pretty much it. So we got all the advantages from the previous approach, and we got the maximum speed. But in this case, there's no kernel debugger anymore. That means that the patch guard shows its face and tries to spoil the fun. So in this case, we would actually spend even more time taming the patch guard, like trying to disable it, right? So if you think of the code that would be necessary to implement this approach, it would be, I don't know, like, for example, 100 lines of the plugin payload and 1,000 lines to disable a patch guard. Yeah, it's like not the exact numbers, but just to get an idea. So obviously I chose the second approach because I love kernel debuggers. And so the goals were to implement the shellcodes. That means to implement the custom page fault and debug trapper fault handlers. Then I would have to locate the space in Windows kernel to place the shellcode. Since I'm operating in a debugger, I cannot really allocate the target operating system memory. I would have to find a place to place the shellcode inside the target Windows operating system. Then we load the shellcode. By that, I mean just copy the shellcode using the kernel debugger and patch the operating system IDT entries. IDT is like interrupt descriptor table. This is the way you set the interrupt handlers on Intel platform. Okay, and here goes the most interesting part. how do we implement the custom page fault handler? So as I said before, when SMAP violation occurs, a page fault is raised. So that's why we actually need to implement the custom page fault handler. But why? There is already a page fault handler in the operating system, right? Yeah, but Windows does not really use SMAP. So it is not aware that we're actually going to use this feature. So it would basically break the system execution at some point. Because, yeah, it is not supposed to catch SMAP violation. That's why we need sort of a wrapper for this page fault handler. By that I mean we have our code that is supposed to decide whether it was an SMAP violation or not, log the data in case it was an SMAP violation, and in case it was not, we would just return to the original page fault handler because, yeah, I really don't want to implement the original page fault handler from scratch because it's kind of complicated thing. And the algorithm is, for sure, check whether the page fault was indeed an SMAP violation, and that is achieved by checking the error code of the page fault. I got like a couple of screenshots. I will show you like at the next slide where those are located. To check, of course, whether the fault happened in the kernel space. So it's pretty obvious because we're tracking the kernel mode references. And check if CR2 register is a user address. CR2 register is a register where the address of a page fault is kept. So for example, if there was a page fault trying to access a virtual address 123, a page fault happens and this register will keep the value of 123, right? So it's basically the way we found out what memory was referenced. So the next step is to disable SMAP by setting the RFLAGS access check flag. So as I said before, there are two instructions like stack and clack which do this. But it's like for obvious reason we cannot use those because we're in a different context when the page fault happens, right? So what we do is we take the thread that caused the fault and we modify the flags of it for it to suppress the SMAP violation as we resume its execution. Then we log everything we need. The saved RIP, as I said before, is on the stack. The CR2 register is in CR2 register. We use RDTSC as a timestamp because it has like high precision, enough to track the time window of double fetch. I mean, not double fetch, two consecutive references to a user mode memory. And yeah, actually we can log there anything else because we're operating in a debugger. We have the access to a symbolic information. We can resolve any kernel variables, so we can log them right away with no problem. Yeah, I should have put this one into the advantages of the second approach, yeah. Because we have the kernel debugger and we have all the symbols, cool. And yeah, the next step is just basically to turn the hexadecimal representation of our information into a string because we have to show a string eventually to the debugger. And since we're operating outside of the debugger context, we have to use the kernel mode function that are already there. And for that, I chose VSprint, which is there to format the string with the needed information. And then I'll just call the DBG printx function, which prints data to the debugger. So yeah, then we set trap flag for the thread that caused the SMAP violation. Why? Because the idea is to get a single step. So, as I said before, we have a piece of code that triggers the SMAP violation. Okay, we logged that one, but how do we skip this and move on to the next instruction? We just temporarily disable the SMAP by doing this, by setting a C flag. And we also set the trap flag. So the next time it will receive an execution quantum, it would issue a single step exception. And then, yeah, this one is most important. I don't know if I don't think you see it, but it's basically an obvious step is to get out of a page fault handler, right? It's obvious. Yeah, and this is the picture I was talking about, because the devil is in the details. So this is the stack layout with privilege level change. But yeah, it doesn't even matter if the privilege change was in place or not, because the stack layout would be the same. So we got the error code for the page fault. And this is the error code encoding for the page fault. The problem is there's no bit in here that would actually tell us that it was an SMAP violation. Like, imagine the situation when, for example, a user mode, a kernel mode thread was trying to write something into a user mode memory, but this user mode memory was protected to be read-only. And we're not really sure the page fault was because of the memory was read-only or because of SMAP violation. There's really no way to find out using the error code. That's why I needed some additional checks, like, for example, whether the faulting code was the kernel code, whether the faulting address would be the user mode address. But for this case, which I described just now, it doesn't work as well. So for some cases, you have to actually extend the logic of your page fault handler. For example, in this case, I had to page walk the target address and to see whether it was read-only or it was not read-only. Because if it was not read-only, then probably it was an SMAP violation. But yeah, anyways, it was a user mode, it was a kernel to user reference, right? So yeah, I think I should log it. But it doesn't really answer the question whether it was a double fetch vulnerability related case. But still, this is something you have to check manually after all. And just for the references, the RIP, which is like instruction pointer of, which shows where the page fault happened, is here as well on the stack. There's also like a stack pointer, but I don't really see why it might be useful, but still it's there. And this is the value of the flags register we're about to patch in our custom page fault handler. So when we do the iRedQ instruction, which is like resume from the interrupt, we just restore this set of registers, and with this set of registers, the faulting thread would resume, right? There's another thing. If we remember the eFlags register, where's that? The access check, alignment check, access control. There's interesting thing about this one. I'm not really sure why Intel used this flag to use it like with SMAP feature, because this bit in the RFLAGS register has also a different meaning, because you see it is called alignment check or access control. So the way it operates, it actually can issue the alignment check exceptions as well. The way it works is, if you operate in user mode this time, you're in user mode, and you set this flag, when you try to access some structure on an unaligned address, for example, if you reference like the word like 4 bytes, but it's not aligned to a 4 bytes, the target address is not aligned for 4 bytes, and access check, not access checks, alignment check violation would occur. And the thing is, Windows actually utilizes this feature. So to enable this feature, we also should modify the CR control register 0 bits. I don't remember which bit, but still, it is set on Windows. So basically, if we set the alignment check or access control bit in flags, it would issue the access check violation. But yeah, in our case, it's not that of a problem, since we're trying to find the kernel mode references. And for kernel mode, this thing doesn't work. It works only if you're in user mode. So it's kind of weird to me why two different meanings are used for the same bit in a RFLAGS register. And by the way, here's the trap fault flag. Yeah, I found you. So we've set the trap flag because we need to single-step defaulting instruction. And that is also the reason why we have to write our own custom debug or trap fault handler, because if we don't do that, we're operating in a debugger, right? So every time we set a trap flag for the faulting thread, it would break into the debugger, and you would have to resume the execution manually every time, which is, by the way, a nice feature if you want to track the references manually. And I actually used that like a couple of times. But if you want to automate this, you need a way to actually resume the execution automatically. And that's why we actually do this. So basically, we reset the trap flag in the RFLAGS, so the next, so then the following execution of the thread will not issue the single-step exception, which is cool. And we enable SMAP back, because we have disabled SMAP in the page fault handler, right? So we have to like disable it, single step, and enable again. And this is how we do it, basically. And yeah, a little detail for the debug trap fault handler. In the first version, I was like, yeah, whatever, I will just patch it away, like the whole debug trap fault handler, so it would resume automatically all the time. But then it was a problem for me, because I needed to trace the different places of code in the kernel, and when I tried to single step something, it just and it skipped, because yeah, I disabled the single step automatically. So I was like, yeah, I need a way to actually find out whether I need to resume or I don't need to resume. And that's where the RFLAG register saved my day again. Because I don't know in advance when I'm supposed to resume execution because it was an SMAP related stuff, or it was something else, like single step in the debugger. I don't know in advance, right? So I kind of cheated, because I remembered I have a spare bit in the RFLAGS register, and it's identification flag, which is cool. This one is used to find out whether your CPU supports the CPU ID instruction. So if you're able to modify this flag, cool, your processor is new enough to support the CPU ID instruction, which means it's like 20 years old. But still, I use this flag for a different purpose. I use it to distinguish whether it was my fault or someone else. So basically, in a page fault handler, I set this bit to disable SMIP, this bit to enable single stepping, and this bit to tell my custom debug or trap fault handler that it was me, and you should resume this one automatically. Yeah, and that actually made a trick, and it worked, and I was happy. Yeah, and I found something, but I cannot tell about this. And about locating the space for our payloads. The problem is, as I said before, we cannot actually allocate memory in the debugger. We're out of context of the target operating system. So I was like, I'm gonna use something that is already there. And I like this one, the user shared page. So this is the one that is mapped to on every process on Windows, and it keeps some auxiliary stuff like what? Like system time, interrupt time. No pointers, unfortunately, that would leak the kernel mode layout. But yeah, just auxiliary data. And it's a page, so it's like 4K in size. But the structure with all this information is a lot less. It only occupies the half of the page. So wow, I have the whole another half of the page to do all the stuff. And it is located at a fixed address. It doesn't care about KSLR, but that's not a big deal because there are no kernel mode pointers or any sensitive data, so which is also cool. And it will not be reused. It is just used for only this, like only storing this auxiliary data. What I mean by this will not be reused is if I take some, I don't know, pool allocation, I would not have control over it because as the operating system executes, someone would, I don't know, decide to free this allocation and then reuse for something else. It would overwrite my code, and you got the idea, right? So I need something more reliable. But since it's a data page, it is not executable, but it is not a problem as well since I have a kernel debugger. So what I do is I page walk it, and I reset the execute disable bit in the page table entry. And that's how it becomes executable. As I said before, it is mapped in every Windows process, but it is mapped in a different way. So it is like one page, but it has different mappings. One is for kernel mode, which I make executable, and the other one is the user mode. Yeah, it might be stupid to talk about security in this case, since I patch everything out, but still, for a user mode mapping, it will still remain not executable. And this is an excuse for me. So we just load our code there, our custom exception handlers, and we store our data there. So yeah, it worked out eventually. And yeah, one thing about this page. So while I was developing this one, I thought like, hey, wait a minute, it is mapped in every user mode process. So what I can do is actually not to send the collected data to the debugger, but the different process, like in a different thread, might be monitoring this area. You got the idea? So since we store the data before sending to the debugger in this user shared page, we can as well monitor it from the user mode on the target system. That would increase speed, but yeah, it would lose some events because we cannot really monitor this at the same rate that we would log the data. And we would definitely not get the double fetch related events because they're so close to each other. We would have to win the race somehow. I don't know even how. So yeah, but it's also an idea. If you need to track just references from your target driver to the user mode structure, yeah, that would work. But yeah, still I use the login to the kernel mode debugger. And what I did is different modes of execution. First of all, it's just automatic mode. It just logs everything and it puts it into the debugger. The manual mode, as I said before, we can skip patching the debug trap of whole handler, and in this case we get the manual way of tracking the references. And in this case you don't even have to look up the output data because your debugger just breaks in to the place where the SMAP violation happens, and you can like explore it from there. Because imagine this, actually I will say just a couple of slides. So the manual mode, yeah. And we have a target module filtering. That means that I do not log everything. I log just a specific driver. I define the range, the address range of my target driver, and I just filter it out in my custom page fault handler, which means it works fast, which is cool for my case. And yeah, I wanted to show this screenshot. It's a WINDBG output. You see, it's not really like human readable. You have to know like what those numbers mean, because the problem is I have the half of user mode, user shared page, the half, but it's still not a lot. So I cannot do the huge pretty string in there because I have a very limited amount of space. That's why I just like do the output for these 4 hexadecimal values, and that's pretty much it. And in this case, you have to post-process this data. So you have like the reference to user mode address, the kernel code that actually touched it, the RDTST value, and the access, whether it was writable, whether it was a write access or a read access. So what you need to do then is to match those addresses to the actual points in the code. So for example, if we have like defaulting RIP, we would have to look up the symbol to know the exact function that caused the violation, right? And for here, we also have to match it to some structure user mode to get an idea what we were referencing. But yeah, in the manual mode, we have an advantage because the debugger does everything for us. It would just break in the point of violation, and it would resolve all the addresses automatically. So you just like look at it. Oh yeah, it was an info leak. Yeah, which is, I didn't even say, but it also can be used for info leaks, because when kernel mode driver puts something into user mode memory, yeah, it might be an info leak, and it happens a lot. So yeah, it's a cool feature after all, basically. Yeah, and that's pretty much it about it. So if you have any questions, you are welcome to ask them now. Smiley Rodrigo face.